Hello everyone, my name is Dario Rexin and I'm working on the Swift compiler at Apple. I'm here today to talk about compact value witnesses in Swift. Now before I get into details about how to make value witnesses more compact, I'd like to talk a bit about what value witnesses are. Swift has a very powerful generic type system. There are different ways to implement generic types in programming language. Some languages do it by creating all objects on the heap and then raising the actual type. So at runtime, there are only opaque references. So a generic function like this would compile down to this. Sorry. Other languages use a technique called monomorphization, which means creating specialized versions of all generic functions with the particular types applied. So if somewhere in a program a function gets called with an integer, the compiler creates a copy of the function with the type fixed to integer. Since Swift supports and encourages the use of value types, type erasure was not an option. Another big focus of Swift is ABI stability, while still allowing types to evolve if necessary. That means that monomorphization is also not feasible, because it would require a stable type layout. This is where value witnesses come into play. There are a handful of value witnesses that the compiler generates for each type. Those functions are responsible for copying, moving, and destroying objects. Witness functions are stored in a value witness table, together with other information about the types, like its size, stride, and alignment. As in this case, a generic function does not receive ownership of its arguments. It does not have to call any witnesses to manage its lifetime. Unless it passes that object to a function that takes ownership of it, in this case, the object needs to be copied first. The compiler will generate the necessary code for us. I'm showing the code here in C++ instead of IR for readability. The compiler added an additional parameter to the function that contains the metadata of t. Through this metadata object, we gain access to its value witness table. We ask the witness table for the size of the object, create a stack allocation of the given size, and copy the object into the newly allocated memory by calling the initializeWithCopyWitness function before we pass it on to the next function. To take ownership of an object, we mark the parameter as consuming. If a function owns an object, unless it transfers the ownership again, it has to eventually destroy it. Again, the compiler generates the necessary code. At the end of its lifetime, we clean it up by calling its destroyWitness function. So we know how value witnesses get used now, but what do they look like? Take this struct as an example. It has two stored properties, an integer and a reference to an instance of a Swift class. The destroy value witness for this type looks as follows. Since integer is a trivial type, it does not have to be destroyed. So the only thing this witness function needs to do is to decrement the reference count on the reference stored in y. The initializeWithCopyWitness does a bit more. It copies both properties from the source into the destination and then increments the reference count of y. Assign with copy is basically a combination of destroy and initialize with copy. An assignment implies that the destination has previously been initialized, so we need to destroy the value it contains first. Just like in the destroyWitness function, we do that by decrementing the reference count of y. Then both properties are copied into the destination and the reference count of the new y gets incremented. For generic types, the compiler has no way of knowing the full layout of the object when generating the value witness. Just like in the generic function example, it has to call through the value witnesses of the applied types at runtime. So in the case of assign with copy, since x is still known to be an integer, it can be copied the same way as before. But for y, we have to call t's assign with copy witness. The metadata of the type parameters of a generic type can be retrieved from its metadata. Now that we have a bit of an idea what value witnesses are, let's look at their impact on code size. Bringing back our non-generic struct, this is the generated ARM64 assembly code for the witness functions. They take up 208 bytes in the binary, and this is a very simple type. Let's add another type that contains an optional value of the first one and another reference to a class instance. The value witness for the new type are 328 bytes in size, and that is in addition to the 208 bytes of the first type. So in total, we're now at 536 bytes. And these witnesses get generated for every non-trivial type. And this is the reason we started looking into making value witnesses more compact. Our requirements for compact value witnesses were, they obviously had to be more compact. We wanted them to be runtime instantiable to eliminate the indirection in generic types. They had to be fast, and they had to be compatible with the existing value witnesses. Instead of executable code, we emit a compact representation of the object layout, which we call a layout string, that will be interpreted by a set of runtime functions. A layout string starts with a header consisting of flags and the size of the operations in bytes, followed by the operations. Layout strings are packed to make them smaller, but also easier to parse and instantiate at runtime. We have a number of different kinds of references in Swift. There are, for example, references to native objects, which can be strong, unknown, or weak. On Darwin, we also have Objective-C references, which can be references to regular Objective-C objects, blocks, or Objective-C objects that are bridged into Swift types. And we have unknown references, which can be either native Swift or Objective-C references at runtime. Looking back at the example type from earlier, the only information required to implement the 6 value witness functions we're looking at is the type of the reference and the offset to the reference, relative to the previous reference or the beginning of the object for the first reference. In this case, we have a strong native reference, represented by the opcode 0x02, at a 1-word offset from the start of the object. We're currently encoding this in a single 64-bit value, where the most significant byte is used for the reference kind and the rest for the offset. There's still potential for improvement here. Instead of using a 64-bit value, we could encode the offset as a variable-sized integer by storing the offset in a single byte instead, and using 1 bit as a marker for additional data in the following byte. So for this particular case, we would reduce the size of the offset to a single byte, and we expect that for most offsets, it will fit into 1 or at most 2 bytes. In addition to the reference and its offset, we also need to store the amount of bytes for any remaining data after the last reference. This is encoded as the opcode 0x00, which also acts as a terminator for the layout string, followed by the number of remaining bytes. So in this case, it would just be 0. But if we had any additional plain values after the reference, it would be the combined size of those values. And then there's the header I mentioned before. So using this compact representation, instead of 208 bytes for the witness functions, we're looking at only 32 bytes now, with the potential to reduce it even further to just 20 bytes. Enums are a little more complicated than structs. We have a number of different kinds of enums. There are enums with no cases at all, enums with only non-payload cases, basically your C-style enums, enums with only a single case, and that case has a payload, enums with a single payload and one-to-many non-payload cases, and enums with multiple payloads and zero-to-many non-payload cases. Empty and no payload enums are always trivial, so we don't generate layout strings for them. The same is true for any enums that don't contain any references in their payload. The memory layout of a singleton enum is identical to that of its payload, so the layout string will be the same as well. There's one more special case. Enums with a single payload case that contain a single reference as a payload and have a single non-payload case, for example, an optional of a reference type, is layout identical to and the only way to express nullable references in Swift, so we treat them as such. Which leaves us with single and multi-payload enums that contain references in their payload. For enums, we are also looking at two additional value witness functions. Get_enum tag, which retrieves the tag associated with the enum case, and destructive inject_enum tag, which stores the tag. The reason we need these witnesses in Swift is that Swift, whenever possible, utilizes uninhabited values and unused bits to store the tag in the payload of an enum to avoid allocating additional memory. For example, on 64-bit Darwin platforms, the first 32 bits of the address space are unused. So empty cases in single payload enums are represented using those uninhabited values, while any valid value in this position means we have a payload. If more space than the number of available uninhabited values is required to represent all tags of an enum, extra memory will be allocated after the payload. Because of the added complexity, even this fairly simple-looking enum comes in at a whopping 480 bytes for the 8 value witness functions we're looking at. To handle a simple single payload enum in a layout string, we need to know at which offset the member storing the extra inhabitants is and how many bytes are used. We also need to know if there are any extra tag bytes. We use at most 8 bytes for the extra inhabitants and at most 4 bytes for the extra tag bytes, so we can encode those two values in the most significant byte and use the rest for the offset. We also need to know the size of the payload. In this case, there are extra tag bytes to read, which are appended after the payload. Because the extra inhabitants don't always start at 0, we also store the value of the first non-payload case and the number of non-payload cases, so we can identify the particular case we're looking at. We also store the number of bytes used for the payload operations and the skip value. These are required to skip forward in case of a non-payload case. And at the end, we store the operations for the payload. As you can see, layout strings for enums are a bit bigger, but we're still reducing the size from 480 to just 88 bytes. Now we know what compact value witnesses look like, but how do they get interpreted at runtime? As I mentioned earlier, we have a set of runtime functions corresponding to the generated value witness functions that interpret the layout strings conceptually. Conceptually, they all work the same way. We start by reading an opcode in its offset. A non-zero offset means there is trivial data between the previous and the current reference, so we have to copy that data. Next, or if there was no offset, the offset was 0, we interpret the opcode. For each type of witness, there is a separate dispatch table that contains pointers to the respective functions for each opcode. For example, if we're executing the destroy witness, the entry for a native strong Swift reference would point to a function that calls Swift release at the current offset. If the opcode is 0, we are done. Otherwise, we continue with the next one. Most of the opcode functions are very simple. For references, it's just copying and incrementing or decrementing reference counts. Enums are more complicated. Let's look at the single payload enum case. First, we read the enum layout information. If it has extra tag bytes, we read them and check if they are non-zero. If they are, this is a non-payload case, so we skip the payload and are done. If they are 0, we check if there are extra inhabitants. If there are no extra inhabitants, this is the payload case, so we interpret the layout string for the payload and are done. If there are extra inhabitants, we read them and check if they have a payload. If we do, we handle it, otherwise we skip. If we don't have extra tag bytes and there are no extra inhabitants, this layout string is invalid. If there are extra inhabitants, we handle them as before. As I said earlier, one of the goals of compact value witnesses was to remove the indirection of recursively calling through the witness functions of generic properties. This is done by instantiating compact value witnesses for generic types at runtime. We already instantiate the metadata of generic types when they are first requested in runtime. So we're utilizing the same mechanism for compact value witnesses as well. To instantiate a layout string, we iterate over all properties of an object and get their type metadata. If the type is trivial, we don't have to handle it directly, so we add its size to the current offset into the object and move on to the next property. If it is a reference, we add the opcode for the respective reference kind to the layout string and continue with the next property. If the type has a layout string, we copy it into the current layout string, which results in a flattening of the combined layout strings, thus eliminating the previously required indirection. We also have to be able to work with types that are not compiled with layout strings enabled. So if none of the other conditions apply, we fall back to calling through the witness table. For that, we emit a special opcode together with a pointer to the type metadata of the property. The runtime function will then read the metadata pointer and call the appropriate witness function. There are a few more special cases that are left out to keep it simple. For example, there are some situations where we store relative pointers in the layout string and they have to be resolved at instantiation time. Another important factor is compatibility. And by that I mean both compatibility with the existing value witness infrastructure, since that is part of the ABI, but also ensuring that we can still evolve this feature and adjust the format of the layout strings if necessary. For compatibility with regular value witnesses, we're using the same value witness tables. For types that are not using compact value witnesses, the entries in the witness table point to the generated witness functions. And for types with compact value witnesses, they point to the shared runtime functions. But we need to access the layout string from within the runtime function. We're already passing the type metadata into the witness functions, so it seemed reasonable to store it there. The metadata has a header that contains a pointer to the value witness table. The metadata pointers that we access at runtime point to the beginning of the actual metadata, so the header sits in front of the actual object. So without breaking any existing assumptions, we can add the pointer of the layout string in front of the witness table pointer. Because type metadata that was generated with older compilers do not have this extra pointer, we also had to add a flag that will only be set when a type has a layout string. The flag is guaranteed to not be set for all existing type metadata. For statically generated type layout strings, the solution is to keep the existing runtime functions and add new ones for any incompatible changes. So the witness table generated for an older compiler may look like this one generated by a newer compiler like this. But they can coexist in the same application. We also need to be able to instantiate layout strings from different versions. Looking back at the instantiation diagram, we have two options. We could check if the versions are compatible and call through the witness table if an incompatible version is encountered, like we do for the types without layout strings. That is not ideal, because it adds indirection, but it would be a simple working solution. Another option would be to translate the layout string to the newer version, which would add some overhead to the instantiation, but benefit runtime performance. Lastly, I want to talk about impact on runtime performance. Since we are replacing natively executable code with an interpretive version, some performance hit is expected. For our simple struct, for example from earlier, we're looking at an approximately 15% performance hit, and that is when executing the witnesses in a tight loop. Since we're instantiating layout strings at runtime for generic types, performance should be identical to non-generic types of the same shape. For this particular case, we're seeing a runtime performance improvement by about 10% compared to regular value witnesses. In real-world experiments, we have found that compact value witnesses reduce the overall code size by up to 10%, while improving application startup time by 5 to 10%, with no perceivable impact on performance. Before I end my talk, I would like to especially thank Gwen Mittertrainer, who created the initial draft for this feature, as well as my colleagues for providing their help and feedback. And I don't have a timer, so I don't know if we have time for questions. We do. Okay, good. Any questions? Mhm. I'm just going to repeat the question for the recording. So the question was if it would be useful to use profiling to determine very hot types, so types where the value witnesses are called very often, and to avoid creating compact value witnesses for these cases.
Yeah, for like select very specific, very high.
Yeah, I think it always depends on the use case, right? I mean, you can't really say upfront what performance will look like. So would always be best to measure performance, and you can certainly compile specific types without this feature enabled. It would maybe be interesting to add some kind of attribute or whatever to say, hey, please don't do this for this type. We don't have that today, but it would certainly be possible.
Okay.
Yeah.
All right, if there are no more questions, let's give Dario a big round of applause.